Okay, so good afternoon, everyone. It's really great to see so many people attending today. Welcome to the second seminar of the LEEPout series of presentations focusing on cutting-edge research in environmental economics, hosted by the LEEP Institute at the University of Exeter Business School. My name is Michela Faccioli. I'm a research fellow in environmental economics at LEEP. And I will be co-chairing this talk with Professor Ben Groom, who will formally introduce our speaker in a minute. Today we have the pleasure to host Professor Thomas Turner from Gothenburg University, who kindly agreed to present his research on climate economics. Many thanks, Thomas, for accepting the invitation. And today's presentation, including Q&As, should last for about 1 hour. So before we start, I just wanted to go briefly through the housekeeping. So we kindly invite every participant to please keep their microphone muted and their videos off during the duration of the talk to avoid interference and bandwidth issues. We will try to keep most questions for the end, but also welcome any clarification request or burning question during the talk. So please make use of the chat box to type your questions or comments as they arise. The chair will select a few questions, and if yours is picked, we will invite you to please ask your question directly to Thomas by unmuting yourself and, if possible, turning on the video as well, which I think will be nice to see some people and some faces. When asking your question, please briefly introduce yourself by saying your name, your role, and the institution you are from. During the Q&A session, you may also want to use the raise your hand functionality, which can be found at the bottom right of the chat box to signal that you want to ask a question. You should all be aware that this seminar will be recorded and that the recording will be made available subsequently on our webpage. Hopefully at this stage no one is experiencing technical issues, but if you do, we recommend that you try to rejoin the meeting now. I will also copy-paste a short version of the housekeeping code of conduct for this presentation in the chat box as a reminder during the presentation. Now, I'd like to leave the floor to Professor Ben Groom, who will introduce Professor Thomas Turner. But before doing so, I would like to take the opportunity to extend all of LEEP's warmest welcome to Ben, who will soon be joining our research group at Exeter as the chair in biodiversity economics. Ben, the floor is yours.
Thank you very much for the kind introduction, Michaela. Very good of you. Well, it's my great pleasure to introduce Thomas Turner to the LEEPout seminar series to kick it off. Thomas is known to all of us, of course, as one of the most important environmental economists in the world, I'd say. And he's done work in all manner of areas, and will have certainly caught most people's eye when he wrote a very famous paper after the Stern Review called the Even Sterner Review. See what he did there. He's worked. I first got to know Thomas back when I was doing my PhD, just at the time when he had written a very important book about environmental policy instruments called Policy Instruments for Environmental and Natural Resources, which still remains a go-to resource for all applied environmental economists. He's worked as the chief economist and the Environmental Defence Fund and the EDF. He also is importantly involved with the EFD, which is the Environment for Development Group, which does sterling work in developing countries and has put a lot of undergraduates from developing countries through masters and PhD programs over the years. And Thomas works on biodiversity and all manner of other environmental issues. And today he's going to talk to us about climate change, which is one of his other key focal research topics. Thomas, it's my great pleasure to introduce you. Take it away.
That was very kind of you, Ben. Thanks so much. I love the introduction. And now I'll see if I am successful in getting this technology to work. Oops. There's something doesn't want to collaborate here. Sorry
I should
about that.
say one more thing while you're doing that, Thomas, is
You can
that
go on giving me compliments, and I'll try to get the.
yes, indeed. The talk will last for approximately 45 minutes. We'll take questions at the end. We can take questions during the talk only for clarification purposes, and so hopefully that's okay with everybody. All right, take it away, Thomas.
Thanks. There we are. Right. Can you all see my screen now? Well,
Yes.
assuming you can. It's
Okay.
you can answer for everybody
I
else.
can see it. I think that means everyone else can.
Yeah.
So to the right is a picture by the Norwegian painter Munch, which gives a good expression of many people's feelings about climate policy. And to the left are some of the species that are causing the problem here. So I hope, I'm assuming it's a big group of economists, and so typically we are sometimes weak on the natural science, and these molecules here, notably carbon dioxide and water vapor, they intercept the long wave radiation when Earth gets hit through a very energetic high frequency radiation, and then in order to remain in equilibrium, Earth has to emit heat as well, and it does so through heat radiation of a longer frequency. And many of these molecules pick up some frequencies. I pick up the energy in this heat radiation. It's partly because the wavelength is just sort of excites these molecules so that they bend or oscillate the shape of the molecule, and they pick up some of the energy in the molecule itself, in the bindings you see there, and then shortly afterwards they emit it, and they can emit it in any direction, so some of it gets emitted back to Earth. And so this sort of this process is well known for a couple of 100 years by physicists, and it explains why an increase in the content of things like methane, nitrous oxide, carbon dioxide, why that increases the temperature of Earth. So let's see. Anyway, temperature on Earth has gone up almost a degree by now, compared to the sort of pre-industrial average. And I'll say something about the coal cycle here. Most of the carbon, that should be carbon cycle instead of coal cycle there. Although, I mean, coal is an important source of the but the confusion there is, someone help me translate. And coal is, the words coal and carbon are almost the same in Swedish. So anyway, the carbon, there's a lot of carbon in the atmosphere, and an increasing amount, but the big reservoirs of carbon are in the soil, in biomass, and particularly in the oceans. And then, of course, there are reservoirs in the fossil fuel that we're extracting, putting into the atmosphere, and then when we put them into the atmosphere, they gradually get absorbed again. And so this is actually interactive. It's difficult here. I can't even see any faces, and So normally I would use the Mentimeter. I would take a break. I would, get everybody to, and it's kind of fun to do this. So I just ask you to reflect, to activate your brains. Reflect on this. Where does all the carbon dioxide go? You can choose. It could go out. It could drift out into outer space. It can be decomposed. It could be picked up by plants. It could be picked up by something else. Where do you think it goes? And here I'll show you where the carbon comes from, the carbon dioxide. 88% of it comes from burning fossil fuel, but a big 12% comes from deforestation and land use change. And none of it goes out into outer space. None of it decomposes. It is the end product of all decomposition. It is a chemically very stable molecule. So methane, which is another cause of climate change, that does decompose. In fact, it decomposes into water vapor and carbon dioxide. So it could have been, but it just isn't, right? It doesn't decompose. It's very stable. The things, it can be picked up by plants and turned into starch and sugars and the building blocks of life, or it can be dissolved into water, into the oceans. And then eventually, but that's extremely slowly, it can also mineralize into rocks. That's a very slow process. A sort of a fundamental sort of rule of thumb to remember is that if we have a doubling of the CO2 concentration, that leads to something between 1.5 and 4.5 degrees of warming. We don't know exactly, but that's the best guess. And if you look at this diagram, this is the most long-run diagram I'm going to show today. In fact, it's economists always like to talk about what's long run. This is 500,000 years here. And you can see that sometimes we've had concentrations of about 180 parts per million. And now suddenly, sometimes we had 180. Those were the ice ages, in fact, quite long periods. And where I'm sitting here, I'm in the Swedish countryside, but we had about 3 kilometers of ice here during the ice age. So we don't really want the ice age back. It'd be very bad for our property. The interglacial, I don't know if you can see my cursor, but I'm putting it, can you see my cursor? Can someone say yes?
Yep, we can see that.
Good. So this here is an epoch, right? The thickness of this line is a few thousand years. And during this epoch, the Holocene, that is when human civilization has developed, the last 5,000 or 10,000 years or something, and we've had about 280 parts per million. And then in the blinking of an eye, the last 100 years is extremely short by geological standards. We've suddenly jumped to 414. Carbon content of the atmosphere has jumped a few times in the geological record. You can see by the order of magnitude of 100. But that's usually taken 10, 20,000 years. Now we've done it in 100 years. Just during the period of time that I've been lecturing about this, the carbon content of the atmosphere has gone up about 70 or 80. So I've sadly come to the conclusion that my lecturing is not enough to stop this. We're now at 414.14 at the moment, but it's ticking upwards. And the IPCC, which I work for the fifth assessment report. It was a monstrous amount of long meetings, week-long meetings in faraway places, thousands of people writing a book that is thousands of pages long. It's a unique effort in human history to do this every now and then, every 5 years. There's no other problem that gets this amount of attention. And the IPCC, for anybody who doesn't know what it really is, it's just a review of the literature. But it's a very, very thorough review. Anyway, the IPCC did a special report on 1.5 degrees. I'll say why I'm juxtaposing these two photos in a moment. But this here is a photo of Bill Nordhaus receiving the Nobel Prize in economics. In the same day, the morning, we had the special report of the 1.5 degree report by the IPCC, which gave strong support to the Paris agreements, saying that it is indeed feasible to strive to be, keep temperature increase below 2 degrees and pursue 1.5 degree target, and that the costs of so doing looked like they would be lower than the extra costs of allowing 2 degrees of warming. In the afternoon, the Nobel Prize in economics was awarded to Bill Nordhaus, and not only Bill Nordhaus, but I'm just going to talk about Bill Nordhaus today, for integrating climate change into long-run macroeconomic analysis. And I personally got involved because media called me and interviewed me, and I was on television in the evening of that day. And they asked me about Bill Nordhaus, and I said the usual sort of pleasantries about what a great scientist he is, what a useful model DICE is, what a service to humanity it is that this model has been developed, and that most people use it in the debate. And then I got some question about, isn't there any problem about this? And I couldn't quite stop myself and say, well, one small problem is that it has supposedly an optimum of 3.5 to 4 degrees, whereas the IPCC this morning just said we should try to stay below 2 degrees. And that's a gigantic, chasm. And this is a diagram that is from Bill Nordhaus, and it shows a couple of curves. There's a base case, which is just a linear increase. There's Bill Nordhaus's, the triangles there are his optimum. And then there's a 2 degree path down in green, for instance, and a 1.5 degree path that Bill Nordhaus says. So this is this contradiction is sort of what has been the driving force behind writing the paper that we're talking about now. And this is the same diagram, but it goes all the way to 2150 here. Sorry, I've got something over here that I need to turn off. There we are. So you can see that Bill's optimum, it does go to 3.5 degrees by 2100, so it's often characterized as a 3.5 degree path, but it actually goes to 4 degrees before 2150. And What happened there? I don't know why it closed. Sorry about that.
You stopped sharing your screen, Thomas, somehow.
I didn't do that, but
Here it comes.
yeah.
Cancel that.
Yes, but I'm not in presenter mode anyway. I think I'll stop sharing it and just put it in the usual mode first. Sorry about that.
Yep.
It's not
You might have to do it the other way around, Thomas.
Yes, I got it to. Now I just need to do the sharing again. Where's there's the share screen, and there is. No, it's still not in.
There we go. We're there.
Mm-hmm.
Thanks, Thomas.
Mm-hmm. Yeah, well, this is so. Anyway, the IPCC characterizes 4 degrees as a disaster, more or less. I mean, very high risks to multiple ecosystems. This is an iconic IPCC figure that has actually been a part of dating back, I think, to the second or third assessment report. And if you read here, you see that for 4 degrees we're in the red region with very significant risks. Many people characterize this as a complete disaster. I mean, the truth is we don't know like what 4 degrees would be like. There's no experience on Earth of this. Certainly, risks are enormous. So, there we are. That's another one. So, I should say, by the way, that Ben Groom is also an author of the paper I'm talking about. I've been a bit careful about talking about this paper because there's an embargo on it, and it will soon be published, but is not yet published, so it's not to be spread around. But all difficult questions will eventually be sent over to Ben. Now I'll be talking a little bit broader than just this paper because it builds on a number of papers, and I have a few other co-authors who I also wanted to mention there in various related. Here's a list of papers that are related to this, notably one on damages here with Peter Howard that was in the ERE 3 years ago, and some discounting papers that I'll talk more about later. I should say here on a personal note, you see the paper by Azar and Sterner there in 1996. I've been thinking about this problem for 24 years. That shows either that I'm a slow thinker or that it's a very big problem. That paper, the Azar and Sterner paper, was also motivated by essentially the same thing. We were looking at Nordhaus's work. Nordhaus at the time advocated a tax of $7 a ton, and his similar sort of value for optimal temperature of 3-4 degrees, and we thought this can't be, so we welfare function issues, inequality and discounting as the main culprits. But in this paper, we have basically collected a large number of things. And there's at least three things that are sort of natural science issues. So there's problems with the carbon cycle, the energy balance models that Nordhaus is using in the DICE 2016. There's problems with the assumptions of non-carbon gases, and problems with discounting, and problems with the damage function. And so, one or two more things. And then this paper is about putting everything together. So, bear with me. Not only is this paper being done in a strange way here by Zoom, it's also 35 papers in one. So I won't be able to go into depth on everything. But I do want to say, first of all, that there's many things I do agree with Bill Nordhaus about, and he's the fact that this paper criticizes his work shouldn't detract from these agreements. One of them is that the carbon price is the best instrument, and another is that DICE is a useful tool, and there's more points of agreement. I'll just skip one or two things here and say something. Basically, DICE is a coupled economic and climate model. There's a maximization of utility. Welfare is produced by using labor and resources. There's a discounting. Output can be used to reduce emissions, but that reduces consumption today, so there's a choice. And in principle, DICE strives to maximize welfare. The welfare function is sort of constant elasticity utility model that I show here. I think actually the current version maybe does optimize over more than 100 years. I'm not certain, but I think maybe 200 years. In temperature. Of course, that's based on a few studies, and I'll come back to that in a moment. This is a big and it's actually a small climate model, but it still is big enough to be complicated, and the precise conclusions that Nordhaus draws are very sensitive to a number of key parameters. And reasonable people can and do disagree on appropriate parameter values. And I've discussed quite a few of these issues with Bill himself. And he's always very keen to discuss them, although with one exception, doesn't generally change his mind very easily. Anyway, the first thing I'll go through is the damage function, and that actually is an area where I think he is a little prone to being open to changing his mind. Then there's the carbon cycle energy balance, the non-CO2 gases, negative emission technologies. Then there's a whole discussion of ethical parameters of discounting. So I'll start with the damage function, and this is actually builds on work that I've done before. Let's see how I could characterize this simply. When Bill Nordhaus was, starting up research on dice. Let's go back to early 90s or something. He needed a damage function. And there wasn't much research on this, so he did something that I think is a very reasonable thing to do at the time. He did a back of the envelope calculation, and there's no disrespect intended, but I think he looked at the list of sectors and thought, which sectors are going to be affected by climate change, agriculture maybe, And anyway, he selected a couple, and then he did some informed guesses, and he did the back of the envelope, and this was the first damage estimate. Then a few other people started doing this, but in fact, the number of people who have kind of been in the damage industry business is really small, and it's particularly dominated by Glenn Nordhaus himself and Richard Toll. And there are more people, but Toll and Nordhaus, with their associates, stand for a very large number of the papers. So what typically happens if wants to do an update and needs a new damage function, then he looks at the literature, and while the literature consists of his own first study, and then a study by Toll, and then 2 or 3 more, and so he does a little summary of these, or takes the average, or does something more sophisticated, and that becomes a new study. And then this process is sort of repeated numerous times, where people sort of go back and look at the earlier studies and summarize them, or take averages, or do a meta-analysis or something more or less sophisticated. And fast forward to today, or 2016 or something, and there are somewhere between 20 and 50 studies, and you could take an average of them. And taking an average of old studies is a pretty reasonable thing to do. But there is a problem, of course, if the average in the end consists of a number of studies that are your own studies. In some cases, like the first study, gets represented several times. It's an observation in itself because it's the first study. Then it has influenced, let's say, the third study or the fourth study, and then the 10th study. And so you see that there's a sort of a multiple publication bias issue, or a authorship bias issue. So what Peter Howard and I set out to do, and I should say Peter Howard deserves a lot of the credit for this, is to study very carefully what are the rules for doing meta-analysis. It turns out that meta-analysis is a discipline and a sort of an art or a science of its own, and people have developed rules, and this includes how to weight older studies, or studies that are more partial, or studies that are by the same author, or studies that have possibly turned up several times, like originally once, and then being a part of a second study or a third study. So what we do is a very careful meta-analysis, where we try very, very carefully to abide by rules for which studies should be included, which studies should be excluded, how you should weight studies, sometimes I just give seminars just about this paper, and there isn't really time to do that today. But here we have a diagram showing. I heard some noise there. Can you hear me still? Okay, everybody? I should have sped up already. But you can see here one of Toll's recent estimates that another Toll estimate that actually finds benefits to warming up to 2 degrees. And you see the DICE 2016 damage function here, which has something like 10% damages to GDP with 6-degree warming. And here you see the estimate Howard and I have. And I should say that this is, I've been, as I said before, there's nothing personal about this. I like Phil Nordhaus, but I've been criticizing a number of papers in various ways. And this is the response, the critique that he seems to agree with most. So, in fact, he did incorporate our damage function in his Nobel speech, and noted that if you believe in this damage function, you get between 0.5 and 1 degree lower optimum temperature. So I'll turn quickly to some natural science problems in DICE 2016. One of them is that the carbon cycle and the absorption of carbon dioxide in the atmosphere, in the oceans, and in biomass is strongly nonlinear. This is a diagram from a science paper by Hughes et al. And it shows what happens if you emit a giant pulse of carbon dioxide into the atmosphere. The black line, that's a pulse of 10,000 gigatons of carbon. Or if you just eject a little bit of carbon into the atmosphere, which is the red and orange lines at the bottom. And you can see that if you emit a little bit of carbon dioxide, then a rather large fraction of it will be absorbed. If you emit an enormous amount, much less will be absorbed. Nature just doesn't have time to absorb it. Let's put it that way. Right, you're disturbing some equilibria between the ocean and the atmosphere, and it just they can't. The oceans can't absorb all this. So you get a smaller fraction of carbon is absorbed in a high carbon scenario. Now, I'll skip some of the numbers. He's calibrated, it's a linearization of a much more complicated nonlinear model. So it's a simplification. And Bill Nordhaus has very reasonably chosen a linearization which is appropriate for the scenario that he believes in, which is the 3.5, 4 degree scenario. If you have that much carbon in the atmosphere, then the absorption will be slower. Now, if you try to use this carbon cycle representation, linearization, to judge the feasibility of a 2 degree world, you get the wrong answer. And that's the trouble with using DICE 2016 to judge the feasibility or optimality of a 1.5 or 2 degree scenario, because you can the model then overestimates the difficulty in reaching these goals. In fact, with the correct carbon cycle model, you can emit more carbon and still get to 2 degrees than you can in DICE. So that is a sort of a factual error when you're looking at a 2 degree scenario. That's one problem. Another problem is in the carbon cycle. I'll go to this diagram here. The absorption, DICE is overestimating the short-run response and underestimating the long-run response. There's a correct sort of equilibrium value of how much the temperature increases with a certain carbon pulse, but the time profile is not quite correct. The third thing that we modified, which is perhaps more of a modeling choice, not really, there's nothing wrong with this, but what is optimized in DICE is the amount of carbon dioxide. The other gases, like methane, for instance, are just entered exogenously. And the values that Nordhaus enters are rather high. And our reasoning is that if you're doing everything humanly possible to get close to 1.5 or 2 degrees and really drastically reducing carbon emissions, then you would logically also be reducing nitrous oxides and methane and whatever other, HCFCs and other pollutants as well. So we choose a lower path for these non-carbon forces. Summarize a number of things that we changed in DICE, and I think in the interest of time, I'll just go over. I've said this carbon cycle model, the energy balance model, and the non-carbon gases. We also introduce, there's technologies that will suck carbon out of the atmosphere, like carbon capture and storage, and they can give negative emissions. And we assume that this will be available earlier than what Nordhaus assumes. Finally, for the economists, we have also a different view on discounting. And discounting is sort of putting a price on the future. The arithmetic power of discounting is enormous. I think you know that if you have 3% discounting, which is roughly what Nordhaus has, then a cost of 20 billion in 100 years' time would be just 1 billion today. The cost of something in 200 years' time is completely insignificant. So discounting, it's very numerically very important, and it's one of the biggest uncertainties we have. So it's we shouldn't blame the physicists for not telling us exactly the equilibrium temperature response or something. The biggest uncertainty in these calculations is actually in the domain of economics. It is what is the correct discount rate, and that's it's partly a matter of good economics, but it's also partly a matter of ethics. So it's hard to decide. One thing many of us agree about is to use something like the Ramsey model, which in its simplest form is the pure rate of time preference delta plus the growth rate of the economy, the expected growth rate of the economy, G, multiplied by the electricity marginal utility, eta. There are more complicated versions of the Ramsey formula as well, where you take into account precautionary motives, for instance. There's the risk or the variation in the growth risk, in the growth rate. Between project risk and growth risk can be important. One of the simplest things, and in fact was the main content of the article I mentioned that I wrote in 1996 with Christian Azar, was that we assumed that there would be a declining growth rate. In fact, there's a lot of evidence that there is a declining growth rate in the world, and if you have a declining growth rate, then you see immediately that you get a declining rate of discount as well.
Thomas, sorry to intervene, just to give you a 5-minute warning.
Okay, 5 minutes, right. So I will mention one of my favorites, which is relative prices. And that the idea here is that You might have growth in get faster and faster computers and telephones, but you might not have growth in, let's say, rainforest or ecosystem services. And this requires you then to have a model with at least two sectors, or maybe multiple sectors, and you get different discount rates in different sectors, or possibly relative price change that is counteracting the discounting if you just have one discount rate. So what we did in this paper is that we, and this is actually Ben's work, so I go over it quickly since you're nagging me on time. There was a survey of experts, and we basically used the survey to get values for eta and delta. And you see in the middle of this page here, Nordhaus uses a delta of 1.5% and an eta of almost 1.52, whereas the median view of the experts that were surveyed here was a much lower delta and an eta of 1. So we combined this to give, now it's done that again to me. I don't know what I did wrong there, but I'll stay in this view. Sorry. And go to this diagram here, where we put everything together. We have in this quadrant, the northwest quadrant here, you see the inequality aversion, and the black triangle here is Nordhaus's choice with a pure rate of time preference of 1.5 and an eta of 1.5. The scatter plot shows various experts, and the median is the blue line, which is what we choose. So this gives a path for the optimal, the social cost of carbon would be the optimal carbon tax. The Nordhaus path is in black here, and our median path is in blue, which you see is a significantly higher carbon tax. The result of this is that we get, following the blue line here, a significantly faster decrease in carbon emissions than what Nordhaus gets. And this sort of gray space here is different opinions, but the blue is the median, and black is Nordhaus. The resulting price, the resulting temperature is shown in this diagram, and this diagram was made on the assumption that we had made the other corrections that I mentioned before with the damage and the carbon cycle and so on, just looking at the effect of discounting. Another way of summarizing our results is here, which is, this is quite a dense diagram. We start over here, look at the top black. The temperature change in the year 2100, Nordhaus estimate, and it's 3.5 degrees. Here you can see in this bar here, you can see what would happen if we accept all Nordhaus's choices and just change the discounting. Then the discounting would bring us down to an optimal temperature of about 2.33 degrees. If instead we move and look consecutively at the bars to the right, we get first here the change in the carbon cycle, and then the energy balance, and then the damage function, and then the non-carbon gases, and a couple more changes here, net negative emissions. And then within each of these, you still have the black triangle showing you what Nordhaus's discount assumptions lead to, and what the mean of our experts gets to. And so you see that we eventually get down to, with all the changes we make, we get down to showing that 1.5 degrees is not incompatible with being the result of an optimization in DICE. So if you assume we are correct in all the changes we make about the carbon cycle, the energy balance model, the damage function, non-carbon path, and so on, then if we are also right in assuming that the ethical parameters should be in line with the average of these experts, then in fact it looks like it would be optimal to have limit warming to 1.5 degrees instead of the 3.5 or 4 that Nordhaus has as optimal. So in a sense, we feel that we're suggesting reconciling the economics that was given the Nobel Prize with the Paris agreements, and showing that with these modifications, these two things do not have to be incompatible. Here are the same diagrams, and just with the metrics of for instance, the social cost of carbon, or the number of years until you get complete decarbonization. So, I think
Thank you, Thomas. That was really good. We do have some questions here. Actually, the first one is from Femke Njise. He's asking about maybe Femke is, if he's still there, or she is still there. Perhaps he would like to ask that question.
Yeah. So the question is about innovation. So I just learned that innovation is external to the model. And you said that one of the conclusions you agree with Nordhaus on is that a carbon price, and I assume a uniform carbon price, is sort of the optimum policy. And I think that conclusion very strongly depends on how you model innovation in your model. If you basically have a non-uniform carbon price, you can leverage some parts of the economy where innovation is way more likely.
Yeah, I agree. I'm hesitating a little bit. I mean, I think what we really agree about is that we need a high price of carbon. Now, sometimes there is political resistance that is very formidable, and there might be other reasons too why you don't want to have a high carbon price everywhere. And then, of course, it is possible to start thinking in terms of seeing where is it most strategic to have high carbon price. I think it's a little dangerous. I kind of think that we need a high carbon price, preferably everywhere, if possible. We tend to look very much at the carbon uses we already have, and how we can lower them. How can we make cars run on electricity, solar electricity, and how can we heat houses through better insulation, and so on and so on. We underestimate the fact that if we do all those things, then the equilibrium world price of coal and oil and gas will fall, and people will typically find new ways of using coal, oil, and gas. And so we could, in the next 50 years, find a lot of new technical progress that uses carbon fuels, fossil fuels, in new ways and causes new problems. And so that's the risk if we don't have carbon price everywhere. You'll have people in Siberia building hot tubs outdoors, and you'll have, just in computing, the so-called mining of bitcoins, I think, uses currently about 100 terawatt hours a year. It's like 20 big coal or nuclear power stations of electricity just for us, to make bitcoins, which is basically
Thomas,
yeah.
I'm going to move you on to the next question, which is from Ian. Shall I just read it out, Ian, or do you want to ask it yourself?
So Thomas, great talk. Really appreciated it. I agree entirely about what you're saying about discounting and about damage functions. A simple question. Well, simple to say anyway. Has Nordhaus's work helped or hindered actions to address the problems of climate change?
Well, so I think my own perception as a Swedish European leftist environmentalist, I've perceived him a little bit as as a blockage, as someone who's an authority who's saying yes, climate is a problem, but it's it's a fairly small problem, and yes, we need a carbon tax, but a fairly low one. On the other hand, he has access to people who are CEOs or congressmen in the United States, and in those circles, he is seen as the greenie. If he would have, been putting forward my positions, he wouldn't be taken to listen to him. Now he does reach an audience, and he did get the Nobel Prize. That means that a lot of economists are taking, they realize, climate change is serious. They don't realize how serious it is. So it's hard to say, actually. But I think he is putting forward a radical position in his circles.
That's a very interesting question. Very interesting question, Ian. So, characteristically difficult to answer, I'd say, but that was fascinating. We have one more. Well, another question here from Marion Desquilbet. Sorry if I'm brutalizing people's names here, by the way. Hopefully you know.
Yeah, so Marion Desquilbet from Toulouse School of Economics. So if I understand,
Marion.
If I understand correctly, you are more optimistic than Nordhaus concerning the negative emission technologies. And I know that lots of people think that there is too much hype about these technologies, but that actually they are not going to be able to do much. So your graph seem to refer to energy crops, and we know that if we have more crops, it's detrimental to biodiversity, which is another very impacted thing by the Anthropocene, and that needs preservation. So can you tell us a little bit more about these negative emission technologies?
Yeah. So, one thing that, and it's true, maybe one is biased by I live in a country with more trees than people, and we actually do use a lot of wood, and we use it in a reasonably sustainable way. People have arguments about that too, but I think on the whole reasonably sustainably. And instead of just harvesting the timber to make furniture and stuff, some of the wood roots and branches and stuff is also used, and in quite a conventional thermoelectric plant to make steam and electricity. If on top of that you capture the carbon dioxide out of the chimney, you actually have created a negative emissions technology, because the trees, when they're growing, are taking carbon dioxide out of the atmosphere, and then when you burn it and make electricity, you don't emit that carbon dioxide. Instead, you capture it and bury it. So that's one example of a negative. There are fancier ones where you might have something that dioxide out of the atmosphere, but I think there's no doubt that you can have some negative emissions, whether or not you can have them on a gigantic scale, and what the consequences of that would be, I think, is a subject for research. I think we don't know that yet. And I worry about all the other things you mentioned, like the biodiversity as well.
Thank you very much. We're at 5:02, and I should put my video on. So in principle, the seminar is over, but we can just take one, if people are willing to stay on, just take one more question if we have them. Just message me on the chat if that's. Otherwise, I'm going to ask Ian to come back at Thomas, because I think I cut him off in his prime a little bit there. Would you do that, Ian, or?
But please don't deter anyone else. Honestly,
all right.
I think it'd be good to have somebody else. That's grand. Yeah. Although I will take this
question because I can't type very quickly.
It's Brett. Yep.
Yes. Hi, Thomas. So I don't work in these particular models, but I do work in ecosystem service modeling, and I'm wondering what your thoughts are about what are the key areas in which this particular modeling could be taken forward. So looking at what you've shown us today, there seems to be some serious doubts about some of the modeling directions that have been taken. And if you could sort of build the research program for the next 5 years about what we need to do with these models to make them even better, what would you say were the key areas to concentrate on?
That's a very big and difficult question.
Well, just give me one then.
Well, I mean, I'll give you my favorite that actually we chose not to use in this paper. But when I try to imagine the future, there are people, particularly non-economists, environmentalists, who think that we should stop growth and not have any growth at all. I kind of think there's something better than that. I think we can have growth, but we can only have growth in some sectors. So there's no reason to allow computer games to go on getting funnier and communications to get faster so that we don't travel so much, but meet like we're meeting now. There's also, we could have all kinds of better medical technology to keep people healthier. We could have, there's lots of areas where you can have human and intellectual progress, and that is growth for economists. What we can't have is growth in gas guzzling cars and cement, aluminium, and plastics and all kinds of. So we need to steer growth. We need to have degrowth in some sectors. We need to have less toxic chemicals and less cement and steel and fossil fuels, and more of lots of other things. And this is going to require strong policy instruments, and it's also going to have implications in terms of relative prices. Change the growth rates of different sectors, then the sectors you're changing all the prices in the economy. We need to think more about that. What kind of a future we want, and this affects all kinds of choices about biodiversity, about poverty alleviation, about how we, our vision of development in low-income countries and so forth.
So, do you think that might be one of these issues, is that these models concentrate solely on the externality from carbon and not on these externalities?
Yes, well, I mean, They do assume, they do, I mean, they're monolithic. There's sort of like there's one, it's more of the usual of growth in some sense. They don't really imagine massive redistribution or reallocation of sectors and so on. That's asking a lot of a sector. I mean, it's a tool for discussing or starting up a discussion about climate change, but it doesn't discuss everything. This is an aspect that is missed.
Well, I think that that's a perfect moment to bring the proceedings to a close. So on behalf of everyone, Thomas, thank you very much for kicking off the LEEPout seminar series and for joining. There is a recording of this, which I assume will be posted on the Michaela's about to answer this question.
Yes, indeed.